So today we're talking about analyzing the forces that act on a body when it has been immersed in liquid. What happens to it? A typical example is what you see in that diagram. Now, there are some which could be immersed vertically, horizontally, or like you can see in this case, immersed at an angle. Because this, the one being considered is this gate here. So we'll come back to this. For now, let's look at how that is done. There are some other examples we have there, meaning before we can get there, we need to look at the application. We need to look at first those principles that should start. And this just refers to the definitions that we normally start with. So first of all, when we talk about immersing a body in liquid, the first thing that you see is that there's what we call the total pressure. Here we are going to be using the word pressure to refer to a force. Traditionally, that's what we'll do in this case. And hence, that force will act at a certain point on a body. The total pressure, we're simply saying this is the total pressure force acting on that body for a fluid at rest, as long as that body has been immersed in that liquid. They can carry different shapes, but the principles, the analysis, it's almost the same, except the shapes will have their own way of going about it. Then the center of pressure, here, the total pressure force, where it is acting, that point, that is the one we call the center of pressure. And it will be denoted by letter H because that is representing the height from the free surface of the liquid. Now, here we have an immersed surface. We'll look at three scenarios. The first one is when we immerse this body horizontally. When you do that, it means that the center of your area and your center of the one we call the center of pressure, they have the same value. So that's what we'll see as we do the application. So here we're saying X bar, that's the depth of the immersed surface from the free surface. Of course, that's our depth of the center of area or center of pressure. A, area, omega, specific weight, and also total pressure. So the total pressure is simply omega A X bar. If it is immersed vertically, considering G to be the center of area of the body, and then A, the total area of the immersed surface, then X bar, depth of the center of area, meaning from the free surface to where the center of area is, and the H bar, the distance from the free surface to where that pressure force is acting. Then the total pressure is P equals omega AX. But there's a problem here. This is too general. So what do we do? First, let's take a strip, a small strip of this area, whose thickness is dx, and at a distance x from the surface. The area of this strip is dx multiplied by b. That is our area. So in place of area, we put that one, b times dx. Then the x still remains like that. So we have omega x, b times dx representing the area. Next, you can integrate both sides. After the integration, this p will just become the integral of dp will just become p. So meaning our P, therefore, the pressure force will be equal to omega A X bar. Omega A X bar. Because now, this bar X will now be referring to that one we talked about, with the center of area. Center of pressure, this is the one we've mentioned, the point at which the pressure force is acting. So it is given for this one, which is immersed vertically, it's H equals moment of inertia about the center of gravity over the product of area by X plus again the same X bar. Here we've talked about it, moment of inertia of the figure about the X and all that. Now here, you will see that different shapes may have different formulas to represent. So if I have a rectangle, for IG, it's BD cubed over 12, triangle, BH cubed over 36, a circle is by D4 over 64. Semicircle, you get half of that, and that's what you get. So what if it's inclined at angle theta to the free surface? That angle of inclination represented by theta, you place it there, it will be similar to what we had with the vertical one, but you have to include sine squared theta. So IG sine squared theta over AX plus the same X bar. The others, like the formula for P, remains the same. Let's pick up our examples and we'll end up with three of those. The first example is talking about triangular plate, base area. This is the triangle, 4 meters, and the height, this is rather the base length is 4 meters, the height is 2 meters. Then it is immersed horizontally in water. And the depth from the free surface is 3 meters. So they want us to determine the total pressure acting on the plate and the center of pressure. First things first, this is the triangle. The formula for the area of a triangle is half base times height. So half base times height, in this case, we're saying half 4 multiplied by 2. Of course, these two will cancel, and you end up with the 4, the one we've just found. Okay, so this will cancel with that, and your answer is there. Okay, next, X bar. Because this has been positioned horizontally, it means that you have your free surface there. Sorry. Let me just draw a better one. Your free surface is here. Then you have your liquid in between and so forth. Then your body is actually horizontally placed there. Now the distance from the free surface coming down is the one we've already been given as 3 meters. So there we do not even need to worry because this is horizontal. Specific weight. Look at the liquid you're dealing with. We're dealing with water, and the specific weight for pure water is 1000 times 9.81, which gives us 9810 as standard. So total pressure, we just go back to the formula, which is omega AX, omega 9810, A4, and X is 3. So when you do that, our answer is 117, then 720. Part B was more like a mock question because it is talking about the depth of the center of pressure for a horizontally immersed surface, where we already know that in this case, both H and X have the same value. So there are no need to calculate, we just plant it the way it is. H is equal to X given by the same number, 3 meters. Here is the second one. This one now is the rectangle, 6 meters by 2 meters. Now the way they've immersed it is in such a way that where are we? 6 meter side is parallel to the free surface. 6 meter side is parallel to the free surface, just like that. Meaning this is the 2 meters, this is the 6 meters. So according to the way we denote the formula is BD cubed. And for the data, that's how we arrange it. So we need to find the total pressure and position of the center of pressure. So then A equals 2 times 6, that's our area. Multiply the 2, B times D is 12. B is 6, D is 2. IG, for this type of a shape, we said BD cubed over 12. BD cubed over 12, and the answer comes out as 4. Then X bar. This is the one we've been given here, from the free surface to the center of this body. So it's like 2, because we already have 2 meters up here. These 2 meters up to the top edge of the free surface. But then this one from here all the way to there, from here all the way to there, it's 2 meters. So half of 2 is 1. So from here to here it's 1. 1 meter plus the 2 meters. This is the number you are seeing here as 3 meters for X bar. So we have now X bar, we have IG, we have B, D, and area. Now let's start with the total pressure acting on this surface. Oh, then we also still talking about this standard liquid, which is water. So its value is also 9,810. Total pressure is simply a combination of omega AX bar. So our omega is 9810. Area we were given, our area is 12 X bar 3. So once we multiply those, we get 353,160 newtons. What about the center of pressure? Here, this is simply IG over A X plus X. In this case, we have X bar and the X bar there. We can just do the substitution. IG was 4, area was 12, X bar was 3. So we add the same 3 even there. So what is our total? Our H bar is 3.11 meters. 3.11 meters. That is our H bar. So we found the depth of the center of pressure. Now the two scenarios we've referred to, we have one which was horizontal, the other one which was vertical. The one that comes in between is now the other scenario, which is for an inclined surface. Here we're told a circular plate or pair of 2 meters diameter, it's a plate, is submerged in oil, specific gravity 0.8, highest below the free surface of water 3 meters and 1.5. Now this one you're not going to be given, is something you sketch out. We know that the diameter of this plate is 2 meters. So the centers from the free surface, from the top edge 3 meters and 1.5, they cannot fit this diameter, meaning it's inclined. So that's how come we fit the 2 meters there by keeping it at an angle. So the first height, 1.5, the second one, 3 meters. Because we're referring to that top surface there. Now that we have this, let's continue with our information. We're looking for the total pressure and the center of pressure, the depth of the center of pressure, how much height we're dealing with. So first of all, the area for this circle is pi d squared over 4. So pi times 2 squared divided by 4. Our answer is 3.142. I about G, pi d4 over 64. So our D was 2. When we substitute, we get 0.8378. Sine theta, here, sine theta, what you can see is that we're looking for this angle right here. So what you do is to get these values, because this one we can find, this one we already have is 2 meters. If the total is 3 meters, and from here to here it's 1.5, then we will need to subtract this 1.5 from the 3. That's where we get the 1.5. So this is actually opposite that angle. And remember, why we're referring to this angle? Because this angle that we have here is the same as the angle we have there. So once we calculate this, we've already talked about that. So 1.5 is opposite. This is the hypotenuse, meaning that opposite over hypotenuse, the value, the ratio is sine. So sine theta is this over that. So that's why there you are seeing 3 minus 1.5 over these two. And hence, we now say theta is sine inverse of those values, giving us 48.59 degrees. Now, let's convert from specific gravity to a specific weight. We multiply by 9,810. So it gives us 7848. With this, we have all the information we need now to finish up our work. Oh, maybe first of all, we also have the X bar. The center of our area is half of this. Now, here, half of this is 1. So if we were to say 1, the distance from here up to there, 1 and this. Well, for now, we already have the angle because from here to there, that's 1. Now, how do we get this one so that we can add it to 1.5? So what we are going to do is to say this height, the unknown one, which you can even decide to call y. Y over 1, because this is 2, but half of it is 1. Y over 1 is also sine theta, this being theta. So when you make this unknown the subject, you end up with this 1 sine theta, 1 sine 48.59, because that's the angle we found right there. And your answer becomes 2.25. So basically, one thing you'll see as we go into this is that we do a lot of shaping up, looking at the shape and working according to the shape that we've been provided. That's how we will run along. Total pressure. Our total pressure is the product of omega, area, and X bar. Omega 7848, area 3.142, X bar 2.25. So our answer is 55.482.436 newtons. Let's go for the center of pressure. Our center of pressure is Ig sine squared theta over A times X bar plus the same X bar. Then what I have is just a substitution, sine squared that over the area, then plus the same X bar I have there. This is the same one. Once you do that, our answer is 2.32. 2.32. That's our center of pressure for this one. Now that we've dealt with all those shapes, let's look at one small application package where you can use these principles to design some gate or some valve. Here's our case. So we have a rectangular sluice gate, and what they've told us is that AB, this one, its dimensions are 2 meters wide and 3 meters long. So the length is 3 meters, the width 2 meters. So meaning that from here to there, that is 3 meters. It's hinged at A here, meaning here it's pivoted at that point. Now, total weight of the gate and the weight of the fixed to the gate 343,350 newtons. So what do we need to calculate? What is this height H, which is just going to cause this gate to open? In other words, here, this side, there is water. There is water sitting this other side. But then it's closed because the weight of the gate and other things are attached here according to these dimensions provided. So when they fill up this up to a particular height, this gate is supposed to open because the moment acting about there is going to be overcome by the moment created by this as a result of the pressure force acting at that center of pressure will soon determine. Now that scenario, having understood that scenario, in other words, what we are saying is this gate must open and it's going to swing about here, about this hinge. Swinging open means it will go like this, going up. Why would it move like that? Because the force coming from here could have managed to overcome the weight acting here, which is 343,350. The moment created by that weight overcome, then there we are. So in other words, at a point it is just about to open, it means the two moments should just be equal. We'll come back to that. So let's implant our information. First, B, referring to the width, that is 2 meters. D, the depth or the length, that is 3 meters. With these, you can get the area. 2 times 3, our area is 6. IG, BD cubed over 12, because this is rectangular. So BD cubed over 12, we get 4.5. Weight of the gate, 343,350. Angle theta, 45 degrees. It's already given there. So with this information, what do we do? Let's take them one by one. Remember, our target is just to find H. So there is our diagram. Now, let's look at X bar. X bar is referring to the distance from the free surface all the way to where the weight is centered. So meaning that this one is H, the whole height, minus ED. Let me repeat that. X bar is equal to the whole height, H, minus this distance here, which is ED. Okay. And moving on from there, you notice that your ED, which is this one, ED, is equal to AD minus AE. AD minus AE. This is A to D. Just remove this one. Then you end up with this distance from here to the bottom there. Because that's what we want. So separately, let's calculate that one. If I'm looking for ED, I should just get the whole AD, then I just subtract AE. So if that is true, then my AD is this sine 45. Because I know that AD over AB, this is, by the way, this is point B. Because I know that AD over AB gives me sine 45. So if I have to make AD the subject, what I will have is this AG sine 45. But I don't need to put those letters. It's actually 3 because this is 3 meters. So that's why now you have 3 sine 45. Next, what about this one? We say AE. We already have 0.6 here. So one thing you'll notice is that the ratio between this and that, AE over EG, that's tan 45. AE over EG is tan 45. So if you make AE the subject, you end up with EG tan 45. So that is because EG is 0.6. So from here to here, it's the same distance, 0.6. So 0.6 tan 45, and we leave it there. Now, since we've already found ED, then we need to take this back in there. But before we do that, we still have something to do. The whole of this, when we sum it up, it gives us 1.521. And meaning that ED, that's what we have. It's the whole of it comes to 1.521. So that now gives us the expression for X bar, H minus 1.521. Now, this should ring a bell. Let me take you back. If you look at what we had here, oh, okay, sorry. I've remembered a different one. We'll come back to this. H minus 1.521. We'll come back to this one. Now, the total pressure referring to P is the usual formula, WA X bar. So what do I do? This is my X bar. Area, we were given it was 6. So all I do is just substitute area 6, X bar, that. Then I have this information the way it is arranged here, H minus 1.521 in place of area 6, then 9810. Next, when I multiply 6 by 9810, I have 58860. Then this one, let's leave it like that for now. Then I come to IG. Again, it's just BD cubed over 12. I think this one, I don't know why we repeated. We already found this. It's the one which is 4.5. I think for emphasis sake, our IG is 4.5. Next, what about the center of pressure? Our center of pressure is given by H bar, which is IG sine squared theta over AX plus AX bar. Remember, this is at an angle. So we include sine squared theta. The rest, just the same. So IG, we have sine squared, the theta is 45, area is 6, then X bar is this expression we're just from calculating, which is H minus 1.521. H minus 1.521. Again, I also want you to remember that the pressure force we're dealing with is here. We'll come back, we'll use it very soon. Now, this H bar remains like that, and we can leave it because you can already see something common. This, that, there. Let's leave it in that format. Meaning that what I can just do is perhaps to dissolve this and leave it in a simpler format like that, where 6 divided by what is on top, I end up with 0.375, then this one is maintained in that way. So H bar I have, X bar I have the expression, P I also have. So this is my expression for X bar, this is my expression for P, this is my expression for H bar. So what happens next? Here I need now to look at the shape of my object, that for this gate to open, the moment of this weight, which is W times that, e.g., W times the perpendicular distance should be equal to this force, P, times AH. Let me go through that again. We are taking moments about the hinge here at point A. And if I'm taking moments about this point, I can even do this, extend this behind there. The perpendicular distance for this one is from here to here, which is EG, and is acting downwards, representing a clockwise moment. So I'll say W times EG, or GE is the same thing, because we're just interested in the absolute distances. Clockwise moments is equal to anti-clockwise moments. The other one is this times the perpendicular distance, which is AH, P times AH, or simply HA, no problem, because that is our perpendicular distance. That is what we have there. W times EG equals P times AH. Now, we will start using the tools we already developed. The first thing we can say is that the weight, there's no problem. We have it. It's 343,350 times EG is here, 0.6, which is equal to, if you check, we said P. Our P was 58860. Then in the brackets, we had H minus 1.521. We are multiplying by AH. Now, let's check our diagram. You will notice that sine 45 is AK over AH. If you consider just this triangle here and this right angle triangle right here. So what you have is sine 45 is AK over AH. This is opposite that angle. So this is the angle we're talking about. This is the same 45. So if that is the case, then I can make AH the subject. First of all, I will notice that if I cross multiply, I have AK is equal to that, but I want AH. AH is simply equal to AK over sine 45. In fact, we could have even just made it the subject right there. So let me take this back to here. If I put it back there, the expression, everything else is this. I've just written it back here again. Then I copy this the way it is, just transfer it like that. I have 58860. In the brackets, I have h minus 1.521 was the brackets, multiplied by, then I have now this one, which is AK over sine 45. But then we still have a small area to clear out. There's AK. This is A to K, this distance. Now, when you look at this distance, there are a number of ways we can find it. The only thing is that the center of pressure P, we do not have the exact physical numbers to refer to. So we'll have to refer to some other things we already wrote. So, AK, first of all, let me just make it the subject of the formula so that we get rid of, we smartly work on it. So if I make AK the subject of the formula, it means I'll just cross multiply this, multiplied by what is on top there. Then everything you see here will be our denominator. I leave it like that. I leave it like that, but I have to divide this by whatever is on top, and in the brackets I maintain this because I already have this, which is looking like that. So h minus 1.521, then on top 2.475 over that. That is my equation 1. We leave it there. Then let's check back again. If you look at AK itself, the one we mentioned, this distance A to K, it's actually this distance H bar, which is the distance from the free surface to the center of pressure, from the distance to the center of pressure, then you just remove what is on top. In other words, we are saying AK is equal to H bar minus AC. Let me go through that. A to K is equal to the whole of this distance, which is H bar. Then we remove AC. Now, logically, that is correct. So all we can do now is bring them on, because H bar, we already have an expression for H bar, which is this. We already said H bar is 0.375 over H minus 1.521 plus H minus 1.521. This is just for H bar minus the AC we mentioned, which is this one. Again, since we don't know the AC, we'll play around with the values that we have. We'll make use of the values that are available. So my AC, this AC, this distance from there to there, when I look at it, it's the one now that we refer to this one here. Because what I have is like CD, the total, minus AD. CD minus AD. Check, we already have this. So meaning I can easily find that one. So then this one we're calling CD is H. Then minus, because I know that AD over AB is sine 45. So then if I make AD the subject, or rather, if I make that the subject, just AD alone, it will be AB sine 45. So that's how come now we have H minus 3 sine 45. So the whole H minus 3 sine 45 representing this distance in the vertical here. So when you compute 3 sine 45, you have H minus 2.121. Now, let's finish up with the AK in this case. So since we said AK equals that which is representing the whole of the H bar minus AC, and we have already found the value for AC, which is H minus 2.121. So all we do is put this back there and write the whole equation the way it is sitting here. So I do that. First of all, I've copied this the way it is up to here. Then where there is AC, I've put H minus 2.121. Next one, I can now go ahead and just expand these brackets. And this one, no problem. Positive, positive, that's the same. Positive H, positive, negative, I have minus 1.521. Then negative multiplied by positive, I have negative H. Negative times negative, I have positive 2.121. Positive 2.121. Now here's the interesting part. This is positive H and this is negative H. So these automatically, they cancel each other out. They cancel out so that what you remain with now is 2.121 minus 1.521. So with that, you end up with 0.6. Whereas on the other side, the number still remains like that. Now, check our work. We have this as our equation 1 representing AK. We also have this as our equation 2 representing the same AK. What do we do? Let's equate the two equations. So when we equate them, the second one, the first one was 2.475 over H minus 1.521 equals 0.375 over H minus 1.521 plus 0.6. So all we are going to do is to get rid of this denominator. So what we will do is to multiply both sides by the same. And this is what you get. This side, we multiply by that, meaning this one and this, they will cancel. Then this side, we open the brackets. This times that will mean this will cancel out. Then this times this will remain like that, and we would have to open those brackets. So what I have now is, here it's just 2 point that. Then here, this one is there. Sorry, this is here. Because when you multiply that times that, they cancel. I just remain with 0.375 plus 0.6 times what is outside gives us this same result right here. Then after that, I can now just go the algebra route. Open the brackets, 0.6 times H, this is what I have. 0.6 times 1.521, I have 0.9126. Making H the subject, I have 2.1. This come to the other side, where after multiplying, subtracting, we ended up with 2.1. Then when this comes to this other side, they will add, I remain with 0.6. So meaning whatever I have, I divide through by 0.6 and make H the subject. My answer is now 5.021. That is the height. When this height is reached, the gate will open. So that is how you handle the formula, the question on the gate. Now, when you look at this, basically, if you hate SOHCAHTOA, please go back and recheck your SOHCAHTOA activities. Basically, those they are the basics that you did in year 1. They came back somewhere in year 2. Refer to those because it's basic algebra that is being used to reshape, and refer to that shape using the triangles, and then combining it with the principles that we've just found. Then after this, there's an exercise there and something to open some more gates. As usual, all of them with answers planted. For now, we are going to end our lesson here. As usual, post your comments, reach out if you need to clarify something.